All right, today we're going to tackle a classic networking problem. You know the kind, the ones you always see on exams. Our mission, if you choose to accept it, is to break down all these tricky calculations into steps that actually make sense. Let's dive in. So, have you ever wondered how long a click really takes? I mean, it feels instantaneous, right? But behind the scenes, there's this whole cascade of hidden delays that all add up. We're about to figure out exactly what they are and how to calculate them. So here is what we're going to do. We are going to break down all those hidden delays piece by piece. We'll look at what it takes to find a website's address, load up the actual page, and even send an email. We'll nail down the time for each one step by step. Okay, let's set the stage. Think of this as a network performance challenge. We've got a mission briefing, basically a set of rules we absolutely have to follow to get the right answers. And here they are. These are the rules of the network for our problem. We're given a handful of round-trip times, or RTTs. Seriously, these 5 numbers you see here? They're the building blocks for literally every single calculation we're about to do. But wait, what exactly is an RTT? Well, simply put, it's the time it takes for a signal to go from point A to point B, and for the confirmation to come all the way back. You can just think of it as a digital round trip. And for our challenge, it's our basic unit of time. All right, let's get into it. Part 1 of our mission, cracking the DNS code. Before your browser can even think about loading a website, it needs to find its address, the IP address. It's like looking up a number in a giant phone book. So how long does that take? Let's find out. Okay, so here's the path that request takes. Your computer asks its local DNS server, hey, where's this website? But surprise, the local server doesn't know. So it has to go on this little quest. First, it asks a root server, then it gets pointed to a TLD server for the .com part, and finally it gets the real answer from the website's authoritative server. It's this whole chain reaction, and only then does it come back to you. So how do we calculate the time for that little adventure? Well, our local DNS server had to make 3 of those external trips. And if we look back at our rules, each one of those trips takes 30 milliseconds. So you just do the math, 3 trips times 30 milliseconds, that's 90 milliseconds right there. But hold on, we're not quite done. That 90 milliseconds is just the time it took for the local server to find the answer. It still has to send that answer back to our computer. And that last little hop, that takes another 5 milliseconds. So you add them up, and there you have it, 95 milliseconds. That's almost a tenth of a second that's just gone. And we haven't even started loading the page yet. That's our first hidden delay, uncovered. Okay, now for the main events, actually loading the web page. We've got the IP address, so let's figure out how long it takes to go from a blank screen to a full homepage, complete with 10 images. And then we'll see how a little thing called caching totally changes the game. So let's assume we're starting from scratch with a totally empty cache. Here's the play-by-play. First, we have that 95 milliseconds for the DNS lookup we just calculated. Then it takes 1 full round-trip time to open a connection with the server. That's the TCP handshake. Then another RTT to grab the main HTML file. And finally, and this is the cool part, thanks to something called pipelining, we can ask for all 10 images at the same time, which only costs us 1 more RTT. Pretty efficient, right? Okay, time to plug in the numbers from our mission briefing. We start with our 95 milliseconds for DNS. Now the RTT to the actual web server is 150 milliseconds, so we add 150 for the connection, another 150 for the HTML file, and a final 150 for all those images. And the grand total is 545 milliseconds. Wow, that's more than half a second from the moment you click to when the page is fully loaded. And you can really see how that 150 millisecond RTT to the server is the big bottleneck here. It's the dominant factor for sure. Okay, on to part 3. Let's change the scenario. What happens if we've been to this site before? Now our computer has the IP address and the basic HTML file cached. How does that change things? Let's see. Okay, this is where you really see the power of smart networking. On the left, let's say we have the info cached, but no connection is open. We can skip the big DNS quest, but we still need a quick 5 millisecond check of our local cache. Then we have to set up a new TCP connection, that's 150 milliseconds, and then get the images for another 150 milliseconds. That brings us to 305 milliseconds. Not bad, but look at the right side. If we have a persistent connection already open, boom, we skip the DNS and the handshake completely. We just ask for the images, and that takes only 150 milliseconds. That is a massive difference. It's more than twice as fast. All right, we've spent a lot of time pulling information from the web. Let's switch gears and talk about pushing information out. We're going to apply the exact same principles, but this time we're calculating the delay in sending an email. So, first things first, before our email server can send anything, it has to know where to send it. It needs the recipient's mail server address, which it finds using something called an MX record in the DNS. You know what? The process is exactly the same as finding a website's address. So the total time is, yep, you guessed it, 95 milliseconds. Okay, now for the actual email transfer, which uses a protocol called SMTP. And here's the thing about SMTP. It is very chatty. It's not a single request, it's a whole conversation. There's a handshake to set up the connection, a hello greeting, the mail from, the RCPT2, sending the actual data, and then a quit to say goodbye. Every single one of those steps needs its own full round trip. So yeah, that's 6 separate round trips. And our rules say the RTT between these servers is 100 milliseconds. 6 round trips times 100 milliseconds each gives us a total of 600 milliseconds. Think about that. All that time is just for the 2 servers to coordinate the handoff of one email. And mission accomplished. We have cracked the code. So let's wrap this all up with a final summary. This is your complete scorecard for the entire networking challenge. So here's the final breakdown. You can see the DNS lookups were a consistent 95 milliseconds. A full uncached page load took a hefty 545 milliseconds, but caching dropped that number like a rock, all the way down to 150 in the best-case scenario. And what's really interesting is that the email transaction, at 600 milliseconds, was actually the longest single process we measured today. Kind of surprising, right? You know, if there's one thing to take away from all this, it's that milliseconds really, really matter. They all add up to create that user experience, that feeling of fast or slow we all know. For anyone building things for the web, understanding exactly where these milliseconds go, well, that's the absolute first step to making things faster. So, we saw how caching and pipelining saved us hundreds of milliseconds. But here's the thing, that technology is pretty old, which leaves us with one final big question. What's the next major speed breakthrough going to be? You know, new technologies like HTTP3 and QUIC are already out there changing the game. In a few years, the answers to a problem like this might look completely different. Something to think about. Thanks for diving in with me.